Greetings from the Department of ECE, SJBIT. Today we will look at MWA more problems in Module 2. All problems related to S matrix and S properties, then followed by means ABCD parameters, Z parameters, then followed by E plenty, H plenty, and magic T problems. First, we will start with the first problem, which is given as, let us consider the S matrix of a two-port network, which is given here. It is a 2 cross 2 matrix, S matrix, which is given. It is of order 2 cross 2. You can observe we have 4 components, S11, S12, S1, S21 and S22. They're asking you to find whether the given network is lossless and reciprocal. So to find out that, first we need to observe from the properties. This is from the properties. As we know, if the network is satisfying the symmetry property, then we say that the network is reciprocal. Symmetry property has to satisfy it. Symmetry property according to symmetry property, Sij must be equals to Sji under the condition I not equals to j. As it is a 2 cross 2 matrix, that means you need to verify whether S12 is same as S21. In the given case, which is same as S12 and S21 both are same, 0.9 at an angle of 90 degrees, these two are same. So then you can say that the given network is reciprocal as it is satisfying the symmetry property. The given network is reciprocal. In the same manner, you can cross verify from the properties the given network is lossless or not. So from the properties again, to prove that whether it is lossless or lossy, for a lossless network, it has to satisfy, unitary property. So according to this unitary property, S conjugate transpose multiplied with S must be equals to identity matrix. Or you can cross verify this as for 2 cross 2 matrix. In row wise or column wise, if you consider S11 square, row wise I am considering S11 square plus S12 square must be equals to 1. If any one condition fails, then you can conclude that the network is not the network is a lossy. If all the conditions are satisfied, then you say that the network is lossless. So we'll verify the first condition. So S11 in the given S matrix, S11 is 0.2 at an angle of 90, S12 is 0.9 at an angle of 90. So now we'll substitute that into this equation, then find out S11 square, S12 square. So S11 is 0.2 at an angle of 90 degrees. Because it's a modulus 1, we are considering only the magnitude, no need to consider the phase. So 0.2 square plus S12, which is nothing but 0.9 at an angle of 90. Again, it is a modulus value. Consider only magnitude. So if you take a square of this, which will be 0.2 square, which gives you 0.04, and 0.9 square, which gives you 0.81. So sum it up, which you are getting as 0.85. So as this is not equals to 1, the first condition itself has not satisfied, then you can say that hence the circuit is, or you can say that the network is lossy, or you can say that it is not lossless. And in the same manner, we can cross verify for the other networks. Same problem with different values. Now you can observe second problem. So S parameters of a two-port network, which is given as S parameters of a two-port network given as, they had given S11 as 0.2 at an angle of 0 degrees, and S12 which is 0.6 at an angle of 90 degrees, and S21 which is again 0.6 at an angle of 90 degrees, and S22 which is 0.1 at an angle of 0 degrees. To prove that the network is, you are asked to prove that the network is reciprocal but lossy. So to prove in the same manner, we need to consider for a reciprocal network, it has to satisfy symmetry property. So according to symmetry property, it has to satisfy symmetry property. So according to symmetry property, Sij must be equals to Sji. Condition I not equals to j. So for a two-port 2 cross 2 matrix, S12 must be equals to S21. In this case, both are same, which is 0.6 at an angle of 90 degrees. You can say that the network is reciprocal. So network is reciprocal. Then in the same manner, we need to prove symmetry property. You need to prove the network whether it is lossless or lossy. For that, for a lossless network, we know that it has to satisfy unitary property. So according to that, S conjugate transpose multiplied with S must result in identity. From this, for a 2 cross 2 matrix, so S11 square plus S12 square must be equals to 1. Cross verify that. S11 given the value as 0.2. S11 given as 0.2, 0.2 square plus S12 which is given as 0.6 at an angle of 90. No need to consider 90 degrees. So 0.6 square to be evaluated. So 0.2 square which has to be evaluated as 0.04 plus 0.6 is 0.36. So you'll get this as 0.364, 0.4. 0.36 plus 0.4 you will get. As this is not equals to 1, you can say that therefore network is lossy. So we have proved that. In the same manner, you can find out for n number of networks in the same manner whether the given network is lossless or lossy. So now we'll solve a problem based on same model. We'll try to find out for a mismatched load. The return loss, how to find the return loss for a mismatched load. Next problem, we'll consider the S matrix, which is given as S matrix. Again, it is a two-port network. Of a two-port network, it means you have a 2 cross 2 S matrix. So they are specifying the values as 0.2 at an angle of 0, 0.6 at an angle of 90. Again, it is 0.6 at an angle of 90. This is 0.1 at an angle of 0 degrees. S matrix is given. What they are asking you to determine is, they are asking you to find the return loss. As we had seen in a two-port network, we have different types of losses. You have a return loss, reflection loss, different types of losses. Already we had defined when defining these parameters. So find the return loss at port 1 when condition they have specified, when port 2 is short circuited. So they have connected with a mismatched load. No, they won't specify in the problem whether it is matched load or mismatched load. By looking at the problem, you need to identify. From this, you can say as port 2 is mismatched, port 2 is short circuited, obviously mismatched load you will get. So you can find out the reflection coefficient, so which is K1 for a mismatched load. It is given as, it is not same as input reflected voltage to S11 value. Mismatched load, which is given as which is the reflection coefficient S11 plus this formula we have derived already, S12 square into K2 divided by 1 minus S22 multiplied with K2. So to find out the reflection coefficient at port 1, first find out S11 from the matrix you will get to know, S12, S22 from the matrix you will get to know. So to evaluate K1, you need to know about K2. So K2, it is nothing but the reflection coefficient at port 2. Any reflection coefficient you can express in terms of the load and characteristic impedance as, which is ZL minus Z0 by ZL plus Z0. So in this case, as it is a short circuited load, for a short circuited load, that means load impedance ZL value is 0. By substituting that into the above equation, which gives you minus 0 minus Z0 divided by 0 plus Z0, which gives you minus 1. Okay, so K2 we have determined. Now the rest of values are, you need to substitute and determine K1 value. So now we'll determine K1, so which is S11. S11 is 0.2 at an angle of 0 plus S12 S12 square. So S12, which is given as 0.6 at an angle of 90. So you can write this as 0.6 at an angle of 90. You can find convert that into rectangular form, which gives you J 90 degrees if you have, which gives you J6, J 0.6 actually it is 0.6 at an angle of 90. Better I'll write this. So which will be J 0.6 whole square S11 square, sorry S12 square multiplied with K2. K2 is minus 1 divided by 1 minus S22. S22, the value of S22 is 0.1 at an angle of 0. So obviously you will get this as 0.1 multiplied with K2. So K2 is again it is minus 1. So if you multiply, you will get this value as 0.2 plus, so J square is minus 1 into minus 1 plus 1. So 0.6 square in the numerator. Denominator will be, so 0.1 into 1, same plus 0.1. So we'll get this as 1.1. Okay. So which gives you, 0.2 plus 0.6 square is 0.36 divided by 1.1. If you evaluate the K2, which gives you 0.52, sorry not K2, it is a K1. We are evaluating K1. 0.5273. Then they're asking you to evaluate the return loss, which is in decibels. You can evaluate that as So K2 value, we'll get this K1 value, which we will get it as K1 we are determining, which is 0.5273. Then they're asking you to determine the return loss. So return loss, which has to be specified in decibels, which is defined as minus 20 log of K1. So you can substitute that and you can evaluate. So minus 20 log K1 value is given as 0.5273. So now you evaluate this, so which gives you 5.56 dB. This is the reflection coefficient at port 1. Suppose if I have considered only a return loss at port 1. If I have considered only S11, then in that case we are getting only 0.2. The reflection coefficient range, as we know, which varies from 0 to 1. 0 indicating no reflections, less value indicating there are less number of reflections. If the value is increasing, indicating there are more reflections. So you can observe with a short circuited load, that is with a mismatched load, the values are increasing. I mean, so the value of K1 reflection is increasing. In the same manner, we will take up another problem, which is repeated many times in the previous year question papers. All these are the problems which we are solving are from the question paper only. They're specifying there are two transmission lines. There are two transmission lines of characteristic impedances Z1 and Z2, and they have joined these two at a plane PP dash. At this plane they have joined. And what they're asking you to evaluate is, they're asking you to express S parameters, in terms of impedances, in terms of the impedance, and condition they've specified is when each line is match terminated. Before you solve the problem, you imagine that and you draw the equivalent circuit. Then you can then you can solve the question easily. You can find the solution for the given problem easily. So if I look at, you have a transmission line, two transmission lines. This is first transmission line and another transmission line, and they have joined at plane PP dash. So let us consider this is the plane where you have joined the two transmission line. The characteristic impedance of the first one is Z1 and second one is Z2, and they're specifying each line is terminated properly. That means match terminated. So that means this side I have connected with Z1, Z2, and this side even it is connected with Z1. Then you don't have reflections. You say that it is perfectly matched terminated. So what they're asking you to find out here at plane PP dash, they're asking you to express the S parameters. S parameters I have to express in terms of Z parameters, in terms of the impedances. So now by considering this circuit, you can express. So we know that in general, you can express, or you can say that the incident wave and the reflected waves at port 1 and port 2 will be represented. Suppose if I consider incident wave at this port as A1 and reflected as B1, and in this case incident as A1 here, and here it is B1. Similar manner here you can consider A2, B2. What they're specifying here, we know that in any matrix, if you consider incident and scattering wave amplitudes or incident and reflected waves, they can relate using S parameters as B is equal to S into A. Now we'll start solving the problem. So they have specified output line is perfectly matched. So as output line, that means the Z2 is perfectly matched. Output line is matched. So if it is matched, then you can say that there are no reflections. So A2 is 0. And the input impedance, if I want to determine input impedance at the junction, which is equal to Z2. And you can observe at this point, input impedance of this will be, here you have matched perfectly. So A2 is 0. And at the input side, means at the junction, if I want to observe, input impedance is Z2. And you can observe Z2 will be the load for Z1. It is acting as a load for Z1 also. So now we can define the reflection coefficient S11 at the input side. So reflection coefficient, which is ZL minus Z0 by ZL plus Z0. So ZL is load for Z1 and which is Z2, ZL minus Z0, the characteristic impedance of the first one, which is Z1 divided by Z2 plus Z1. At the plane I am observing reflection coefficient at port 1, here I am observing. For this the load is ZL and for this input impedance is characteristic impedance is Z1. So that's the reason why we get Z2 minus Z1 by Z2 plus Z1. So this is the one reflection coefficient at input side. Similarly, same theory can be applied as it is symmetry. Because of symmetry, assuming that input side is matched with the assumption as A1 equals to 0, you can say that S22 you can determine, which is ZL in that case will become load ZL minus Z1 minus Z2 by Z1 plus Z2. If you compare with respect to S11, it is inverse, means minus of S11. So S11, S22 we have determined. Now left out with S12 and S21. That I can determine by using the generalized formulas of S matrix. So we know that for a two-port network, you can write P1 as S11A1 plus S12A2. Similarly, B2 is nothing but S21A1 plus S22A2. So with output line matched, if I consider as the output line is matched line, so that means A2 is 0. Substitute in that. By substituting that, you will get in the above equation A2 as 0. By substituting this, you will get B1 as S11 A1. B1 as S11 A1 as A2 has become 0. And at the input side, that means for the second line, Z2, that is a Z, as you have a different impedances at the two arms, due to the different impedances at two arms, you can write square root of Z2 B2, which is equal to A1 plus B1 multiplied with the square root of Z1. So you have a different impedances. If you have same impedances, then you can say that Z2 is means these two will be same, which will get cancelled. How we had written this equation means B2, that means at the load side, which you have means whatever has been transmitted to the load, which is a sum of the incident and the reflected, the resultant one, which will be flowing through. Okay, so B2 is nothing but A1 plus B1. As you have different impedances, that's the reason why multiplied with the characteristic impedances. Now you substitute the above equation into this. So B1 is nothing but S11A1. After substituting this A1, B1 is S11A1. S11A1 multiplied with square root of Z1. Now in this case, A1 you take common again. A1 if I take common, 1 plus S11 into square root of Z1. This side you have square root of Z2 into B2. So you can also express B2 by A1 ratio, which is nothing but S21. B2 by A1 ratio, S21, 1 plus S11 multiplied with, you send this Z2 term to the other side, which gives you Z1 divided by Z2. Or you can also express this S21 as, considering S11 into this equation, you can write S21 as 1 plus S11 is the reflection coefficient already we have determined in terms of impedance, which is Z2 minus Z1 by Z2 plus Z1 multiplied with square root of Z1 by Z2. Now you expand this one, so Z2 minus Z1 minus plus Z2 minus Z1. Z1 terms cancels in the numerator, so we'll be left out with in the numerator 2 times of Z2 divided by Z2 plus Z1 first term multiplied with square root of Z1 by Z2. And again you can write this as 2 into square root of Z1 into Z2 divided by Z1 plus Z2. You can write this as square root of Z2 into square root of Z2. 1 will cancel. So this is about S21. In the same manner, you can determine S12. So with the input line matched, one can find, that means A1 we are considering as 0. You can determine by substituting A1 0 into the above equation. You will get B2 as S11 A1, S21 A1 0, then S22 A2. So S22 A2 due to different impedances at the ports. At port 1 and 2, you can write square root of Z1 B1 equals to A2 plus B2 into square root of Z2. Now you substitute the above thing in this equation, which gives you A2 plus B2 is nothing but S2 to A2. So S2 to A2 multiplied with square root of Z2. So now in this equation you take common again A2. So if I consider A2 as common, which gives you 1 plus S22 into square root of Z2. On this side you have, this side you have square root of Z1 B1. Now you can find out B1 to A2 ratio, which is nothing but S12 B1 to B1 to A2 ratio. Now we can determine B1 to A2 ratio, which is nothing but S12 which is given as 1 plus S22 multiplied with square root of Z2 by Z1. Again for S21 you substitute, so therefore S12 will be 1 plus S22 already we have determined, which is Z1 minus Z2 by Z1 plus Z2 multiplied with square root of Z2 by Z1. And again in the same manner, now in numerator we have 2Z1, denominator as Z1 plus Z2 multiplied with square root of Z2 by Z1. So now Z1 which will get cancelled, you'll be left out with 2 into square root of Z1 into Z2 divided by Z1 plus Z2. So all the parameters we have determined. Now you can write down all the parameters in terms of S parameters at plane PP dash of the given two transmission line network, as therefore S matrix will be four parameters you have, that is S11, S12, S21 and S22. So S matrix will be S11 we have got as Z2 minus Z1 by Z2 plus Z1, and S12 we got as 2 into square root of Z1 into Z2 by Z1 plus Z2. And even this we have got same 2 into square root of Z1 into Z2 by Z1 plus Z2. Last one we have got as Z1 minus Z2 by Z1 plus Z2. So this is the S matrix which we have got for the given two-port network. So in the same manner, if they ask any problem, first analyze that, then you understand, then you can represent. Okay. One of the example already we have three problems which we have solved. In the same manner, if they gave a different problem of same kind, you can solve. Next we will solve for H parameters, that is for H plane T, problems related to H plane T and magic T. First we will refer to H plane T problem, then magic T problem. So first consider H plane T, which is given as consider another problem. Shorthand. Given a problem, like it is a problem on H plane T, you can observe. So they are specifying a 20 milliwatts signal. It has been fed into one of the collinear ports. So we know that in H plane T you have 3 ports. It's a 3-port device. Port 1, port 2 are called as collinear ports, and the other port we call it as a H junction or H port. To the collinear ports, one of the collinear ports, they had given 20 milliwatts of input signal, and they're specifying it is a lossless line, lossless H plane T junction. They're asking you to evaluate the power delivered through each port when other ports are terminated with matched load. Specifying they have terminated with a matched load. If I consider H plane T, And here they're specifying A1, which is given with 20 milliwatts of signal, and it is A2, and it is A3. We know A is a incoming and B is a outgoing. Similarly, A is a incoming and B2 is outgoing. A3 is incoming and B3 is outgoing. And as they are specifying, other ports are match terminated. That means there are no reflections. So A2 and A3, according to them, they have specified it is 0, 0. No reflections, match terminated. And you have been asked to evaluate the power delivered at port 2, port 3, port 1, 2, 3, all the 3 ports. Now first to evaluate the power, effective power at input port. For a H plane T, we know that already the S matrix. Just recollect the S matrix of a H plane T. So which will be, it is a 3 cross 3 matrix. You can find this as S matrix of H plane T. Which is given as 1 by 2 minus 1 by 2, 1 by root 2, and minus 1 by 2, and it is 1 by 2, and it is 1 by root 2, and 1 by root 2, 1 by root 2, and it is 0. And from this you can say that S11 value is given to you. So S11 value, it is known to you as, from the table you can say that S11 is 1 by 2. It is giving the reflection coefficient at port 1. So if I want to determine the power output at port 1, so total effective, so reflected power you have as well as incident power you have. Effective power at port 1, input port, which is given as, so P1 is equal to incident power minus reflected power. Incident power minus reflected power. So incident power is, you can express in terms of A's and B's as half A1 square minus half B1 square. You can also express this as half you take common, A1 square also you take common, which will give you 1 minus half already taken common, B1 square by A1 square. B1 by A1 is nothing but S11 square. And the incident power is represented, already they had given the power incident at port 1, which is 20 milliwatts, 20 into 10 power minus 3, and evaluate 1 minus S11 square. S11 is half, 0.5 square. If you evaluate this, which will result in 15 milliwatts of power. So 20 milliwatts, if I give 5 milliwatts of reflection, and we are getting effectively into the port 1 as only 15 milliwatts. That 15 milliwatts will get divided into port 2 and 3. If I say that the network is lossless. If the network is lossy, then again the reduction in power will occur. Now we will determine the second part, which is power transmitted to port 3 and port 2. For port 3 first we will determine. So which will be given as power transmitted to port 3, which is half A1 square incident power multiplied with the reflection coefficient at that port, which is S31 square. So already this part we know, which is 20 milliwatts, 20 into 10 power minus 3. S31 from the S matrix, which is given as 1 by root 2 whole square. So which is 1 by 2, 20 by 2, so 10 milliwatts of power has been transmitted. Similarly, we can determine the amount of power transmitted to port 2 is given as E2, which is incident power of A1 square multiplied with the corresponding reflection coefficient square. So S21 square or S12 square. So P2 will be this part, which is 20 milliwatts, and from the H plane T matrix, S matrix, S21 is 1 by 2, so 1 by 2 square, which gives you 20 by 4, which is 5 milliwatts. And you can observe in the diagram, as we had seen, 20 milliwatts if I give input, only 5 milliwatts which will be reflected back, only 15 milliwatts effectively it is entering into the port 1. So that 15 milliwatts divided into port 2 and port 3 as 5 milliwatts and 10 milliwatts respectively. Okay. So in the same manner, we can see another problem on H plane T junction. Or we'll do that in the next class, then stop. Thank you. It got hanged up.